Let's take a look at another sample problem. In this one we're asked what the specific heat of lead is if it requires 635 joules of heat to raise the temperature of 100 grams of lead by 50 degrees Celsius. So as always we first want to write a data table. Here we're given our heat value. Q is equal to 635 joules. The mass is 100 grams. The specific heat is what we're trying to find, so we have a question mark there. And our change in temperature is 50 degrees Celsius. It's being raised, so notice that the Q, or the heat value, is positive. Our base equation here is our specific heat, C subscript P, is equal to our heat in joules, represented by Q, divided by the product of our mass times the change in temperature. So on top we'll have 635 joules. On the bottom we'll have our 100 grams and 50 degrees Celsius. It's very important here that you keep the order of operations correct so that you get the correct answer. And the way that I do this is I would take my joules, 635 joules, Q, and divide it first by the mass of 100 grams, hit enter, and then divide that value by the 50 degrees Celsius and hit enter again. This will keep you sometimes from the order of operations mistakes that come from mistakes in using your calculator. So when we do this, notice that none of the units cancel, and we're left with a value of 0.127 joules per gram times degrees Celsius. Well, we solved for heat, we solved for specific heat. Now let's solve for a final temperature. In this problem, what is the final temperature of 75 gram sample of water at 30 degrees if we add 525 joules of heat to it? So first of all we write our data table. Q is equal to 525 joules. Our mass is 75 grams. Our specific heat of water is the well-known 4.184 joules per gram times degrees Celsius. And finally our change in temperature is TF minus 30.0 degrees Celsius. To solve this problem, we're going to need a bit more of a complex rearrangement. So I first would take my Q and divide it by both my mass and my specific heat. And then I would have TF minus T naught would equal that, Q divided by mass times my specific heat. And then I would add T naught to both sides, so it will cancel out on my temperature final side. And we would have TF equal to Q divided by my mass times specific heat plus T naught. So here we have 525 joules divided by 75 grams and 4.184 joules per gram times degrees Celsius. Now when we do this, our joules will cancel, our grams will cancel. We're left with 1 over degrees Celsius, which is a degree Celsius. We're going to add that value to our 30 degrees Celsius, and we get a final temperature of 31.7 degrees Celsius. So far we've done problems dealing with the specific heat equation. Let's change things up a bit and we'll go to a problem involving latent heat. How much heat must be added to melt a 50 gram sample of ice at 0 degrees Celsius? Now it's real important when we're looking at latent heat that we specify that the melting process, that in this case the ice is starting at its melting temperature. Otherwise we would need to use the specific heat equation to see how much heat would need to be added to bring it up to its melting temperature. So here we're starting at 0.00 degrees Celsius, and we're going to melt the ice and not change its temperature. During a phase change, what is happening is that energy is being used to rearrange the particles, in this case from a solid to a liquid. Liquid particles have a much higher energy arrangement than do solid particles. So rather than the particles moving faster and reflecting a higher temperature during this, the heat being added is, in a very simplistic explanation, the heat being added is going to rearrange the particles and put them into a higher energy state. So we write our data table first. Our Q value is what we're trying to find. Our mass is 50 grams, and the latent heat of fusion is 334 joules per gram. So we're solving for Q, so our base equation is also our working equation. Q is equal to mass times the latent heat of fusion, so 50 grams times 334 joules per gram. The grams cancel, you're left with joules. The heat is being added to melt the ice, so this will be a positive value. And in the correct number of significant figures, the correct answer is 16,700 joules. Let's take a look at a situation where we have steam at 100 degrees Celsius and it's going to condense to liquid water at that same temperature. Again, it's important that that temperature be specified, because if the steam doesn't start at 100 degrees Celsius but is at a higher temperature, then we need to account for the heat that needs to be removed to bring that steam down in temperature until it reaches the condensation temperature. So the problem is how much heat is released by a 40-gram sample of steam that condenses to liquid water at 100 degrees Celsius. Our data table, Q is what we're trying to find, so our question mark is there. Our mass is 40 grams, and our latent heat of vaporization is negative 2260 joules per gram. Now, this is a case where normally when we report latent heats of fusion and latent heats of vaporization, we will always report their absolute value, meaning that they'll be positive. In this case, though, because we are removing heat from the steam in order to get it to condense, we have to have a negative sign in front of our latent heat of vaporization. So it's very important that you know what the signs mean and when to use them. So in our solution, our Q is equal to M times delta H VAP. So we have our 40 grams times negative 2260 joules per gram. The grams cancel. You're left with joules, so you know that you set up the equation correctly. And we get negative 90,400 joules. And you can see tremendous quantities of heat are involved in the boiling or condensation process, much more so than in the melting or freezing process. In our next problem, we're going to solve for the mass of liquid water at 100 degrees Celsius that would be converted to steam if 9,250 joules of heat were available to be added to it. So we want to write our data table first. Our Q, our heat, will be 9,250 joules. This is a positive number because it's being added. Our mass is our question mark. It's what we're trying to find. The latent heat of vaporization we'll use as a positive value here because, again, heat is being added, and it's 2,260 joules per gram. Now, in our previous problem, we were removing heat, so we used a negative value of our latent heat of fusion. We're adding heat here, so we want to make sure that we have this positive. With our data table complete, with our signs resolved, we can go ahead and solve this problem. We're going to rearrange the equation so that our mass is equal to Q divided by our latent heat of fusion, Q being heat. So our 9,250 joules is on top, divided by 2,260 joules per gram. The joules will cancel. 1 over grams is a gram, so we know we set this equation up correctly. And the amount of liquid water at 100 degrees Celsius that can be converted to steam if 9,250 joules of heat are added is 4.09 grams. This is the end of part 2 of the specific and latent heat problem-solving series. We'll end with a quote from Albert Einstein. Question that sometimes drives me hazy: am I or are the others crazy? Good luck. There's more to come.